Okay, picking up where we left off a minute ago about streams, we were talking about the fact that streams have certain sort of formal characteristics, floodplains, levees, cutbanks, meanders, and so forth, river channels, um, and that the water flows a lot faster when it's moving through the channel than when it has to move over the land to get to the channel. So we're going to come back and talk about specifically why that's the case pretty soon. We'll do some calculations, but for now, let's talk a bit about what happens and what we do with the water when it's in the stream. So I'm going to draw sort of an orthogonal view now of a stream. Try and draw a little box here if I can. Oops. Okay, something like that. So here's a stream channel, and the water is right in here, and it's flowing out this way. Okay, so this is the land surface, like that. Okay. So the first thing that probably the two most important parts of a stream that we care a lot about are called the stage and the discharge. So the stage is simply the height of the water level, the height of the water. So it's the water level. And as a result, it's measured in distance units. In the States, that usually means feet, right? So if the stage is whatever, 31 feet, that would be 31 feet above some benchmark level for that stream. So the stage can be, it's a height relative to some datum, some background level, and that can be sea level. If we want to use that overall, could say that in Iowa maybe a stream is at 951 feet, or we could use it a stage relative, say, to the base of the bed. So a stream is at 10 feet might mean there's 10 feet of water above the base of the stream at some bridge or some particular point. And one of the things that's nice about that is you sort of know in a circumstance like that what is flood stage. So flood stage would be the height that the water can rise to just as it exceeds the river channel. So this would be the highest the water could be right here without actually flooding. Once it goes a little bit higher, now it spills out across the floodplain, and it's at flood, right? The other thing that we want to know, as I said, that's stage. The other thing we want to know is discharge. And discharge is also, so I'll write discharge here. Discharge is also known as volumetric flow. So how many gallons of water or boxes of certain size of water are moving down the stream at for every given period of time. Discharge is generally abbreviated as a capital Q, and it has, in the United States, generally has units of CFS, which stands for cubic feet per second. So that would be, let's see, feet cubed per second, something like that. And the way you calculate that's pretty straightforward, right? So if you have I'll just draw our stream again here, kind of as a box. So if you have the stream and the water's flowing out like this, in order to calculate the volumetric flow, all you need to know is how deep is the water, how wide is the stream, and what is the velocity? How fast is it moving? So what you need to know is depth times width times velocity. And if we look at the units on each one of those, right? Depth is in, say, feet. and the width is in feet, and velocity could be in, say, feet per second, which is analogous to when you're driving down the road, miles per hour. So if you multiply feet times feet times feet and divide by second, you get feet cubed per second, which is CFS, right? So it's a pretty straightforward calculation. It's a little bit more complex in practice, but you need to know the cross-sectional area. Depth times width would be the area. The cross-sectional area of the stream, not measured to the stream bank, but measured to the height of the water itself. Cross-sectional area of the stream multiplied by the velocity of the water. Now you remember before that the velocity of the water changes depending on where you are in the stream, right? So water velocity, let's say average water velocity, which is what we really need for that calculation, is a little bit tricky because when you're looking down from space, this is map view, so here's north, right, map view, and here's, trees over here on the sides, and the water's flowing this way. The water's going to be fastest in the center and slower on the sides, right? Because of, as we said, because of friction between the bank and the water. When you're looking at it in side view now, so here's a fish, and here's air up here, and this is the riverbed, the rocks and so forth down at the bottom, right? That's a fish. So the water's flowing, and it's going to be flowing slow down here. It's going to get a little bit faster as we move up. It's going to get a little bit faster, and then it's going to slow down again because of friction with the air. So you have to think of this in sort of 3 dimensions, right? If you just float something, like a little, watch how fast a stick or a little piece of something floats down the river, what you're going to be measuring more or less the velocity of the water at the surface, but that doesn't necessarily capture the velocity, the average velocity of the entire thing. Likewise, if you put a stick over here and watch it float down the side of the river, you're going to be measuring a velocity that's slower than what it would be out in the center. So anyway, there are some pretty simple, straightforward tools that you can, or calculations that you can follow, or methods, I should say, to follow to figure out where to go. But in general, you want to be a little bit down below the top of the stream, and you want to be out in the middle. And you can get a rough approximation for the average velocity. Okay, so the other thing that we should talk about is that because of the fact that there is friction between the banks and the water itself, we get water generally flowing faster when there is more water in the stream. And an easy way to illustrate that is to imagine something like this. So here, here's a stream. Pull this down here. Get rid of that. All right, so think about the water being this deep, right? I'll make it nice and square here. So this is a rectangle. Let's say it's 10 meters across and 1 meter deep. So it has a cross-sectional area of 10 meters times 1 meter, which is 10 square meters. It has a total circumference. Is that the right word? Circumference? I think that's the right word. Of 10 meters plus 10 meters plus 1 meter plus 1 meter, which would be 22 meters, right? Of that, this side and this side and this side are all in direct contact with the bed, right? So we've got 12 meters of water that's in direct contact with the bed, okay? So we can look at the ratio of the area, the cross-sectional area, to what we're going to call the, well, let's just, for now, we'll just think about it in terms of the portion of the water that's in contact with the bed, and that would be the sides plus the base, right? So in this case, we have 10 square meters over 12 meters, right? And I don't know what that would be, 0.9 something. I'll do the calculation in a second. We don't need to worry about it. But let's sort of take this to an extreme end member so that we can do this calculation really easily. Let's say then that this thing was super deep and it fills all the way up, and now it's still 10 meters across, but now it's 100 meters high. Okay? So the cross-sectional area is now 100 meters, that's the depth, times 10 meters across, which equals 1,000 square meters. And the sides plus the base are equal to what? 100 plus 100 plus 10 equals 210. So in this case, we have the cross-sectional area is 1,000 divided by 210 is somewhere around 5. So what we see then is that when the water's shallow, the ratio of the cross-sectional area to the length of the river that's in contact with the base is less than 1. As the water fills up, this ratio climbs all the way up to 5 or so. So what does that really mean? What is that really telling us in terms of the way that this, I don't know if you guys, hopefully I didn't write off the page there. Yikes. I'll put this back. What does it mean that the cross-sectional area relative to the sides and the base is so much greater? What it means is that there's a much higher percentage of the water that is not in contact with the sides. All of this water in here is free to flow, and only this little water around the outside is the water that's in contact with the bed and therefore is being impacted negatively by friction. Okay? So what we can do then is we can sort of generalize. We could say, well, then if that's the case, then as stage increases, what would happen to Q? As the height of, I'm going to draw a little graph here. This is called a rating curve. And rating curves are calculated specifically for different points on different rivers all around the world. Everyone has their own sort of specific rating curve, but we can sort of figure out generically what these rating curves are going to look like. As the height of the water in the river increases, we have an increasingly small amount of water that's in contact with the side. So the velocity is going to be increasing, right? We are at the same time, we are increasing the cross-sectional area, right? So remember that Q is width times depth times velocity. So in our simple model here, the width is not changing as stage increases, right? It's always 10 meters across. The depth is increasing, and the velocity is increasing as well, right? So what's that mean? That means that Q is going to increase faster and faster as stage increases. As the water gets deeper, the volumetric flow is going to be increasing faster and faster. So what this is going to look like, essentially, is this. We start out, we increase the height of the water, and we get sort of a commensurate increase in discharge. But as the water gets deeper and deeper and deeper, we start increasing this term, the depth, but we're also increasing the velocity because less of the water has to worry about being slowed down as it rubs against the side. And so the velocity begins to increase faster and faster and faster, so that when you're way out here, a small increase in stage results in a big increase in discharge.